तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we had analyzed the circuit for the ECL 10K series, which is the commercially available ECL gate. So, just like in the TTL gate you have the advanced gates, here also in the ECL you have an advanced series called the ECL 100K series, where some modifications have been made with respect to circuit, but the major advancement is in the form of technology. We will come to that. First let us take up the circuit aspect. So, on the blackboard here we have the circuit for the TTL gate, sorry, for the ECL gate of the 100K series. Okay. Now, as you can see that the modifications on the circuit, there is a small part here which consists of two diodes connected and with a resistance here. Okay. Now, the purpose of this is basically for temperature compensation, that is the circuit outputs should not depend on temperature. Just I will explain it. That is, you know that in a bipolar junction, in a PN junction, the voltage drop changes with temperature. It reduces in fact by about 1.5 millivolts per degree centigrade or so. Okay. Or 2 okay. So, if you assume that, what happens is if the temperature rises. So, this is the instead of a resistance only as a current source, here you have a proper current source, this is a current mirror type. Okay. All right. So, what happens is if you assume here that the voltage VCS is fixed. Okay. Now, as the temperature goes up, this base emitter drop is going to change, okay, say by 1.5 millivolt per degree centigrade. So, which means that the current flowing here is going to change, okay, the emitter current of the transistor is going to change, and you have a corresponding increase in collector current, which means that the value of the current source is going to change. Okay. Now, if we assume that the left hand branch is conducting, say, that is, for example, if T2 is on, okay, what it means is that there is going to be a larger current flowing through the left hand branch, okay, through this resistance R1. Okay. And if we adjust the current and the resistance in such a way that here, okay, the drop is around, say, of the same order, that is 1.5 millivolt per degree centigrade. Okay. This would exactly compensate the drop here increases by 1.5 millivolt per degree centigrade. This would compensate for the drop change in the VBE of this transistor. Okay. All right. So, this VBE is going to reduce. Okay. So, the output voltage here remains the same. Okay. The drop here goes up, whereas this goes down by the same order. So, this output voltage remains the same. Now, what happens with the other output? See, if this voltage changes, say, by 1.5 millivolt per degree centigrade, with increase in temperature, there is going to be a current flowing in this path. Okay. And this current is also going to increase. In fact, this diode here in this path also has a same temperature dependence, okay, of VBE, of the drop across the diode. So, basically there is going to be a drop corresponding to, say, 3 millivolts per degree centigrade. Okay. And what is going to happen is, if you assume R2 is equal to R4, okay, this, because of this increased current flow, there is going to be a larger drop here across this R2 by the same 1.5 5 millivolt per degree centigrade, that is this 3 millivolt per degree centigrade is going to be divided between R2 and R4. Okay. So, this at this point also we have an increased drop corresponding to 1.5 millivolt per degree centigrade, which compensates for the reduction in VBE of this transistor by the same margin, by the same amount. Okay. So, with the result that the other output also the output remains fixed, okay, irrespective of temperature. So, with this circuitry, all right, basically the temperature variation, okay, with the output voltage variation with temperature is reduced. Okay. So, that is the purpose of this. So, we have an additional circuitry. Also this I have not drawn it, this voltage generation circuits for VR and VCS are properly temperature compensated. So, that these voltages are fixed with respect to temperature. Okay. So, these are the modifications in the circuitry in this series, all right. So, the other modification which you see here is that instead of a 5.2 volt power supply, okay, minus 5.2 volt, okay, this is minus 4.5 volts. Okay. So, the power supply voltage has been reduced primarily to reduce the power dissipation. Okay. So, these are the modifications from the circuit point of view. The other major modification is, as I said, from the technology point of view. These transistors, okay, as in the advanced TTL series also, these transistors are different transistors in the sense that mostly they employ oxide isolation instead of junction isolation, okay, which reduces the parasitic capacitances from the device, and also the device dimensions are reduced. Okay, whereas the original transistors were about 6 micron minimum feature size, this is about 3 micron minimum feature size, and you know that with the reduction in size all the capacitances are going to go down, which will result in better which will result in lower delays, okay, and higher speed of operation. Okay. So, this is the ECL 100K series, which has got superior performance compared to the ECL 10K series, and the data is power dissipation of this gate is 40 milliwatt per gate, and the propagation delay is 0.75 nanoseconds. Okay, and which corresponds to a power delay product of 30 picojoule, which is less than the 10K series. Okay. So, you see that this is real sub nanosecond gate, okay, which has been achieved, okay, and this is available commercially, all right. So, okay. All right. Now, what we have seen is the ECL gate is, well, the speed performance is quite good, that is the propagation delays are quite low, but the major problem with respect to ECL gate is its power dissipation, okay, that is it has got a very large power dissipation, okay, that is the problem with ECL gates, and there has been a lot of effort to reduce this power dissipation. Okay. So, we shall now take up those aspects, okay, how to reduce the power dissipation in an ECL gate. Okay. One of the ways to reduce the power dissipation of an ECL gate is what is to improve the functionality of an ECL gate. By functionality we mean that if we can achieve a more logic function, okay, a more complicated logic function using the same power dissipation. Okay. How can we do it? Okay, we achieve more logic, more complicated logic using the same power dissipation. Okay, that is, for example, whatever with the same power as in an OR NOR gate, if you can achieve more complicated logic, okay, then you would save on power. Okay, all right. So, let us see how we can do it. The way we can do it is by using a stacked ECL gate. So, you are already aware of the stacked I squared L gate. Okay. So, this is a similar concept as such. So, let us see how this works. So, this is our well known NOR gate structure. Suppose we have structure like this, and then we have another emitter coupled structure like this, okay, and this is VR, and basically this is level shifted down by 1 V on, and here also this level shifting is required. Okay, so this is another input. So let us say you have the inputs A, B, C here. Let us say you have the input S here, and this is VR, and this basically would mean it is VR minus V on. Okay, where V on is the drop across the diode. And of course, here also the purpose of this diode resistance combination is to reduce the voltage by one diode drop. Okay, so you have this combination. Okay, so this is for level shifting purpose. So again, you can have the emitter follower as you have normal ECL gate. Okay, and here also can have another emitter follower. Okay, suppose I call this F1 and I call this F2, and here it is ground, there it is minus VE. So this is the circuit of a stacked ECL gate. Okay. Now let us see what is the logic function you get at F1 and F2. Okay. We can just write a truth table, you know, S say, and here we say A or B or C, that is, okay, whether, all right, and A, F1 and F2, the outputs. Okay, that is S. So you have the 4 combinations, possible combinations. Okay. Now, if you look at this emitter coupled structure, the lower part of this stack, okay, then this side the voltages are just level shifted down by one diode drop. Okay. Now, if S is high compared to VR, okay, then the current flows in this transistor T1, okay, and T2 is off. All right. So current flows in T1 and T2 is off. Okay. Now, so the current is flowing in this path. Now, if so, this current is actually acting as the this is now you have a emitter coupled structure here, and the current of this is flowing through this path. Okay. Now, if A or B or C is high, okay, current will flow in this left branch, that is through resistance R1. Okay, and this output F1 will be low and F2 is going to be high. Okay, and if A or B or C are all low, then actually current flows through this transistor, okay, which we may call T3, okay, and F2 is going to be low and F1 is going to be high. Okay. On the other hand, if S is low, what happens? This part T1 is off, T2 is on. Okay, and if T2 is on, the current actually flows through R2. Okay, and this part there is no this is off, so there is no current flowing here. So if current flows through R2, F2 is going to be low and F1 is going to be high. Okay, so what is the logic here? Let us see. 0 0 means S is 0, that is S is low. Okay, that is again that means that T2 is on. Okay, so the current flows through R2. Okay, so F2 is going to be low, F1 is going to be high because there is no current flowing through R1. Okay, F1 is going to be high, F2 is going to be low. Okay. Now, again if S is 0, okay, basically irrespective of what is A or B or C, okay, T2 is conducting, which means that you have the same condition here. Okay. All right. Now, if S is high, okay, that means what is happening is this left hand branch of the lower stack, okay, lower part of the stack is conducting, okay, and T2 is off. All right. Now, in this condition, if A or B or C is 0, that means none of these transistors, all this is 0, okay, that means T3 is conducting, that means current flows through R2. So, F2 is low and F1 is high. Okay. And now, if S is high as well as A or B or C is high, that means current flows through R1, no current through R2. So, F1 is low, F2 is high. Okay. All right. So, what is the logic function? So, F1 is A or B or C NAND of this AND of A or B or C. Okay. So, you see basic idea is, you see in this configuration the power dissipation is the same as that of a just a ECL or NOR gate, because you have the same power here, same only one the current which is flowing, okay, is the same as that of a OR NOR gate. Okay. This is the standard ECL or NOR gate. Okay. The power dissipation is the same, but what you have got out of this is larger functionality. Okay. That is, you can make more complicated circuits, okay, using the same power as that of an OR NOR gate. If you would have to realize this using OR NOR gates, okay, you would have to have more than one gate, okay, which would mean that you consume more power. Okay. So, effectively you are reducing the power consumption, okay, by using stacked structures. Okay. So, this is the whole idea with this. Okay. All right. Now, we shall see more interesting circuits. Okay. So, you can have different combinations, okay, of stacked ECL gates by connecting them in different ways. Okay. All right, and you can get more complicated functions realized. Okay. Another interesting circuit which we shall take up now is that of a D flip flop. Okay. So, you have the two, you have in this circuit you have the clock and clock bar inputs, okay, and then you have the similar structure as we have seen for a stacked gate. This is one resistance, you have another such structure, okay, and you have two more transistors, lower stack. Okay, so this is now one of these inputs goes here and the other one goes here. So, this is basically, this part is basically for level shifting, as you can see, okay, the voltages are shifted down by one diode drop, okay, one p-n junction drop. Okay, these two transistors are for that purpose. To the lower part of the stack, okay, the voltage levels have to be shifted down. So, here just right here the input here, this is VR. Okay. Now, Okay. The output must go to level shifters okay. These are the level shifter transistors. So, this is basically the emitter follower transistors. So, one goes to the base here, the other output goes to the base here, okay, and to the left. So, this one should come here and this one should come to the base of this transistor, okay, and this is going to be Q bar, this is going to be Q bar, this is going to be Q, okay, I think. So, this is the circuit of a D flip flop, okay. Basically, as you can see, the power consumption is going to be almost the same as that of a simple OR NOR gate, okay, because you have one basic gate structure, okay, the same power, okay, except of course you have some emitter followers, okay, level shifting circuits which also will draw some current, but they are quite small currents, okay. So, this is the power supply, okay. So, what you have here is, now you have you know what is a D flip flop. D flip flop has one input D and the other input is clock, and you have Q and Q bar outputs, okay. When the clock is high, then whatever is the D input is transferred to the Q output, okay, and when the clock is low, then whatever was the previous Q output is retained, okay. The output does not change when the clock is low, the output changes only when the clock is high, and when the clock is high, the D input is passed on as the Q output, okay. So, this is a simple level triggered D flip flop, okay. It is not an edge triggered or a master slave. We shall see how you can make a master slave, okay, but this is a simple level triggered D flip flop, that is when the clock level is high, it is going to pass on whatever is the D input to the output, okay. Now, here of course, there is a slight modification in that we require both the clock and the clock bar inputs, okay. You can have circuits which have require just the clock input, but I have taken this because normally, okay, you can easily get the clock bar outputs, okay, especially in ECL gates where any output which you get also the complement of the output, okay. You have OR NOR combinations, okay. So, clock and clock bar will be available, so you have those two outputs. Now, this see these inputs clock and clock bar are level shifted down by one diode drop, and they are fed to the base of these two transistors, okay. And what happens? So, one of them is high and the other is low, okay. Whichever one is high, so if the clock is high, that means this left hand branch is going to conduct, this left hand transistor, okay, call this T1 is going to conduct and T2 is going to be off, okay. So, basically what it means is that this left hand this left hand part of the circuit is going to be operational, while the right hand circuit as such is not operational, okay, because there is no current flowing there, okay. So, if you look at this now, this is just like an ECL gate, okay. If D is high, then this output, okay, again D and V are, these are the two inputs, okay, just like an ECL gate. If D is high, then say we call this T3 and T4, T3 is on, T4 is off, okay. If T3 is on, then the collector of this at the collector of this T3, there is a collector current for T3, which means that this output at the collector of T3, that is low, this voltage is low, whereas the other voltage is high, okay. So, basically you have level shifting here, okay, or an emitter follower structure here. Okay. So, this is q bar. Okay. So, from here you go, this is q bar, okay, and the other one is q. All right. The other thing which you notice is, okay, that this q bar output, okay, which is here, okay, is connected to the base of this transistor, which we call, let me call this T6, and q output is connected to the base of T5. Okay. All right. Now, what happens? Now, suppose what the clock input changes, okay, that the clock becomes low. Okay. Now, let us see. So, initially if D is high, okay, if D is high, Q is high, and Q bar is low. Okay. I think I made a mistake here. This circuit, this will come here, sorry, this will come here and this one will come here. Okay. All right. Please make this change. Okay. This one will come here, this one. Okay. Now, if D was high, okay, initially Q is high. So, this is high and this is low. Okay. But actually these transistors are not conducting because there is no emitter current, because T2 is off. But suddenly if the clock becomes low, what happens is this input is high and this is low. Okay. So, T5 is on and T6 is low, T6 is off. Okay. So, basically the current which was flowing in T3, it will still continue to flow through T5. Okay. And since there was no current flowing in T4, T6 is not going to draw any current. Okay. So, again Q bar will be low, okay, Q is going to be high. All right. So, and you retain the original condition. Okay. So, similarly if D was low, the current would be flowing in this branch, okay, current would be flowing through R2 and there is no current flowing through R1. Okay. So, what happens is Q bar would be low. So, if D was low, Q bar is going to be high, okay, it is connected to this point, okay, and Q is going to be low. Okay. And basically the whole idea is that, all right, when the clock is high, T1 is conducting, you get the output corresponding to this ECL gate. Okay. That is when D is high, okay, Q is high and Q bar is low. Okay. When the and during the at the same point, okay, what you are doing is the same outputs Q and Q bar is fed as inputs to this part of the circuit. Okay. And one of the inputs is high and the other is low. Okay. All right. And so, what happens is if suddenly the clock goes low, then the control is transferred to this part of the circuit, the right hand side part, okay, and here the inputs are such that the currents continue to flow in the same resistance. Okay. If the current was flowing through R1, the current will continue to flow in R1, okay, and so the output really does not change. Okay. If current was initially flowing through R2, when the clock was changed from high to low, current will still continue to flow through R2, okay, and so the output does not change. Okay. Again, when the clock goes high, okay, the control is transferred to this part of the circuit, the left hand part of the circuit, and so the output will depend on the D input. Okay. Depending on what is the value of the D input, okay, the output is going to change. All right. So, this is the D flip flop circuit, okay, and it gives an output as expected for a D flip flop. Okay. Now, in most practical applications, okay, you would want the output to change at one instant of time rather than for the entire period when the clock is high. So, what you have is you have a edge triggered or a master slave type of D flip flop. In this case, it is more practical to have a master slave type of flip flop. The master slave flip flop, what you do is you have another D flip flop, okay, and here if you have the clock, here you have the inverted the clock is inverted and fed as the clock of the second flip flop. Okay. So, what happens is when the clock is high, the output changes with respect to the D input, okay, but the second flip flop is disabled. So, the output, the actual output of this does not change. Okay. Only at that instant of time when this clock goes from positive to negative, okay, at that instant of time what happens is the first flip flop gets disabled, okay, and the second flip flop gets enabled. So, whatever is the output here, okay, of the first flip flop gets passed on to the output of the second flip flop at that instant of time. After that, since the first flip flop itself is disabled, okay, so this, if you call this Q1, okay, Q1 is not going to change anymore, with the result that Q2 is also not going to change, because the D input for the second flip flop is no longer going to change. Okay. So, only at this instant of time, okay, when the master clock, the original clock changes from high to low, okay, whatever is the value of the D input of the first flip flop gets transferred to the final output. Okay. So, that is master slave D flip flop. Here the, if you have a clock, okay, the output changes only at one instant, okay, that is at the falling edge of the clock pulse, it does not change at any other instant. Okay. So, it is in many practical circuits it is advisable to have a master slave configuration, because you want one change per clock pulse. So, how do you do it? Obviously, you must have another such circuitry, another such D flip flop made, okay. And how do you make what changes do you make in that second D flip flop? You have to just change the clock inputs, okay. So, just like you have fed the clock input here at T1 and the clock bar to T2, okay, you have to just change that. You have to feed the clock bar to T1 and the clock to T2, okay. So, that will take care of that, all right, and the D input of the second flip flop is going to come from the Q output of the first flip flop. So, if you have that, okay, you have a master slave D flip flop. Okay. Again the advantage is, see, advantage for this type of gate is that they have much improved functionality, that is you have achieved an entire D flip flop, okay, with the power consumption corresponding to a single gate. Okay. So, that is the advantage you have derived using stacked gates, all right. Okay. So, this gives us some idea of how one can use stacked gates to reduce the power dissipation in ECL gates. In fact, there have been some similar circuit configurations which have been suggested, okay, to improve the functionality. We shall take up one of them now. I mean, in fact, we shall take up two of them. The first one which we shall take up is called the EFL, okay, which stands for emitter function logic. Okay. And this is a sort of derivative of the ECL, okay, and again the idea behind this is to improve the functionality, okay, so that the effective power is used more the power is used more effectively. Okay. All right. So, what is an EFL? We shall take that up first. So, ECL gate, you know, is basic structure is something like this. You have a current source, this is ground, this is the input, this is VR, okay? And this output here, say, is going to different many such gates, all right? So these are the fan outs basically, okay? So you have one more, say, okay, all right. Now in EFL gates, always we use the non-inverting output, okay? The inverting output is not used, that is this output, okay, which you normally the NOR output, okay, this output is not used, okay? So one thing which can be done is that this resistance has no purpose as such, this particular resistance, because you are not taking the output from this resistance, from this collector, okay. So you can remove this resistance, so this can be basically shorted in all the circuits, okay. So this resistance is removed, that is one thing which you can do straight away, because all the outputs will be taken from the non-inverting output, okay, side. The other thing is, here we have seen that we have removed the emitter follower which we were using in the normal ECL gate. We shall see that later on, we shall see that even with that the circuit performs well, okay, there is no problem. I shall take that up later. Now, so with this configuration, now what is done is, suppose I take this part of the circuit, okay, this part of the circuit, I can redraw it as, I have a resistance, I have one current source here minus VEE, this is ground. From this point you have the outputs, okay. So you have, so this is gone to the ground, okay, the collector is gone to ground, and if you look at the fan outs, okay, for all of them the collectors are gone to ground, the base is common, only the emitters are different, the base is shorted, you see, all the bases are shorted, the collector has gone to ground. So what I can use is a multi-emitter transistor, okay, because, all right, as I said, the collectors and bases are all shorted. So this is gives I can redraw this part of the circuit, okay, of the original circuit by this circuit, okay, all right. So this we shall see now. Here what you have is, okay, now that is if I have a logic A here, okay, and if, and here of course it is VR, that is the reference voltage, okay, all right. Now if A is high, okay, if A is high, that means what happens is, if the base emitter voltage of this transistor becomes lower than the cut in voltage, okay, or V on, then what happens, this transistor is off and the output is high. If A goes low, okay, current can flow here, okay, and current flows through this resistance and output is low. So basically the Y, if you write Y here, it is equal to A, okay, we have not achieved anything as such, okay. Now suppose I have this also as a multi-emitter transistor, okay, and I put another input here B, all right. Then what happens? What is the logic there? Y is high, the output is high when none of these emitters are conducting, isn't it? There is no current flowing through this resistance, okay, if none of the emitters are conducting. So, it must be that Y A must be high and B must be also high, then only none of the emitters are conducting and current flowing is 0. Okay. So, this is why A and B. A and B must be high. If one of them is high, then the current flow can flow through the other emitter, and then if the current flows through one emitter, there is going to be a collector current, okay, and the output is going to be low. So, Y is high only when A and B is high. Okay. So, you can have other inputs also, you can make AND gates, but anyway that is not very important. Okay. The important configuration is something like this. You have two inputs like this, then suppose I have structure like this, it is a current source VEE. Here again there is a level shifting done here. So, this is VR, from here you have a diode drop to here, okay, and say let me call this A1, let me call this A2, and this is called capital A. What is the output? That is what is important. Okay. All right, in this circuit. Okay. So, when is Y high? Again, Y is going to be high when both the emitters are not conducting. Okay. All right. When emitter 1 and emitter 2 is not conducting. Okay. Only in that case the collector current of this transistor is not 0, and there is no drop across this resistance, and the output is going to be high. Okay. Now, when is, if you call this emitter 1, when is emitter 1 not conducting? When either A1 is high, or if A1 is low, you see the current has to flow through this. Okay. But if this transistor is off, then also there cannot be a current flowing in this emitter. Okay. So, you say that when A1 is high or when A is low. Okay. When A is low, then this transistor is off. Okay. And for emitter 2, A2 is high or A is high. Okay. If A is high, then current is flowing in this transistor and the other one is off. All right. So, this emitter 2 is not going to conduct. Okay. Okay. So, I want to repeat, if say if you call this emitter 1 and emitter 2, emitter 1 is not going to conduct if A1 is high, which means it just switches off this emitter, because that emitter is not going to get forward biased by sufficiently. Okay. Or if even if A1 is low, okay, if A is low, then there is no current flowing here, there is no path for the current to flow. Okay. So, if either A1 is high or A is low, and for emitter 2 to be not conducting, okay, either A2 must be high or A has to be high. If A is high, T1 will be on and T2 will be off. So, emitter 2 cannot conduct. So, this is the output, logic output which you get. Okay. In fact, this can also be written as, okay, so this is the same as A1 into A plus 2 A bar. Okay. All right. So, this is the logic function. So, you can write it in this way. What you get is, you have one input here, capital A, okay, then you have two outputs here, this two OR gates, and so this is A bar or A1 and this is A2, okay, A or A2 and AND gate. So, this is Y. So, this is what is achieved, okay, in this circuit, all right. And of course, as you can very well see, the current the power dissipation corresponds to that of a single gate, all right, because there is one current source, okay. So, this is the logic, all right. Now, of course, you can make it even more complicated, okay, by just modifying this circuitry, okay. That is, you have, say you put this here, okay, then what happens? What is the change in this circuit here? Instead of an inverter, this becomes a NOR gate, all right. Instead of an inverter, this becomes a NOR gate, okay. You have a NOR and OR, okay, all right. So, the logic which you will have is, this is a NOR gate, okay. You have the two inputs A and B, sorry, this I'll draw it like this. You have one NOR output and one OR output, okay, and again you have the A1 and A2, A1 and A2, F. Again, the power consumption is the same as that of a single OR NOR gate, but you see that you have a very complicated circuit, okay, here, all right, and so you have improved the functionality, okay, that is what is more important, okay. So, this is the circuit. Now, you can make lots of other things like gates, okay. Now, suppose you want to make let us take some example. Suppose you want to take an exclusive OR gate, you want to make an exclusive OR gate. How do you do it? We can come back here, all right. Now, if we make this A1, if we go back here, you know, if A1 is equal to B and A2 is equal to B bar, okay, what you get is, in fact what you get is an exclusive NOR gate, okay, that is you get AB plus A bar B bar, that is an exclusive NOR gate, and if A1 is B bar and A2 is B, okay, you get an exclusive OR gate, okay. So, by changing the inputs you can get different types of gates also, all right, in this case, all right. Now, you can also have a D flip flop, okay. If you look at this again, if you look, Y is equal to, this is the original function which you have, okay. If you look at this function, okay. Now, in a D flip flop, if all right, I think we shall take it up in the next class, okay. That is, we shall see the more complicated circuitry, the D flip flop, for example, how do you realize in using EFL, and we shall also see one thing which we have left out, that is the voltage requirements, okay. That is, we have removed the emitter followers, okay. So, whether the circuit will actually work, okay, because the voltage levels are different, okay. So, what is the voltage levels required to make this circuit work? So, these are the things we shall see, but of course, we can see that this is the functionality is improved tremendously in this circuit. That is, you can make a lot of complicated circuitry using the same power consumption as in a single gate, okay, and that is why this is called emitter function logic, okay, and it's a important variation of the ECL gate, okay, for low power dissipation.